So we are studying about the insertion of dielectric in between plates of a capacitor. Okay, ma? So first of all, what is meant by dielectric? Dielectric is called an insulator. Okay, ma? Insulator is what is called a dielectric. So what is meant by insulator, ma? Insulator means what? So in insulator, number of free electrons are almost zero. Clear, ma? So what is meant by free electrons? The electrons which are responsible for conduction. So if electric field is given, these free electrons, they travel from one place to another place and they conduct electricity. Clear, ma? So these free electrons, they are absent in the case of a dielectric material. Okay, switch on your videos, all of you. Okay, ma. So let us try to understand this one by taking a small example. Clear? See, ma. For example, if this is an uniform electric field, so in one region, consider there is one uniform electric field. Okay. So in this electric field, if I place a conductor, okay, for example, if this is a conductor which is placed in uniform electric field, okay, now can you say what will happen? Okay, so if a conductor is placed in an uniform electric field, already we have studied this one now previously. If conductor is placed in an uniform electric field, what is going to happen, ma? Can you say? What happens is, electric field inside this conductor, it will become zero. This is what happens, no? Electric field inside the conductor will become zero if conductor is placed in an uniform electric field. Clear? So why electric field inside the conductor will become zero? Because conductor, what is the meaning of a conductor? It is a very good conductor of electricity. It means free electrons can very easily travel throughout the volume of this conductor. That is the meaning of a conductor, no, ma? So immediately if I apply uniform electric field, then what will happen? Then what happens is, so initially this will be the direction of electric field. Are you able to understand, ma? This is the direction of induced electric field. So what happens? The positive charges which are present throughout the volume of this conductor, they start shifting in the direction of electric field. It means all the positive charges, they get deposited at one end of this conductor. This is what happens, no? So if all the positive charges, if they get deposited here, what about negative charges? Negative charges, they always travel in the direction, opposite direction to the direction of electric field. So this is the opposite direction of electric field, ma? So all the negative charges, they go and deposited another end of this conductor. This is what we have studied now previously, ma? So positive charges, they travel in the direction of electric field and get deposited here. Negative charges, they will travel in opposite direction to the direction of electric field and they get deposited here. Okay, ma? Now this side has become positively charged side and this has become negatively charged side. So therefore what will happen here? There is another electric field developed inside the volume of this conductor. Clear? And what is this electric field called as? Can you say? What is this electric field called as, ma? This is called as E-induced. This is called as induced electric field. Clear? And in a conductor, in a good conductor, E-induced, magnitude of E-induced is equals to magnitude of E naught. What is meant by E naught? E external. Okay, ma? So this condition is always satisfied. In a very good conductor, what is the amount of electric field which you are applying externally? This is called as E naught, or you can call it as E external field. Okay, ma? So this is always equal to E induced inside the volume of this conductor. So, but this electric field and this electric field, are they in same direction or are they in opposite direction? They are in which direction, ma? So external electric field and induced electric field, they are exactly in opposite direction, no? So therefore what I will say, what is the net electric field, ma? Students, are you listening? You must answer. What is the net electric field inside this conductor now? Net electric field will be E naught dash minus E induced. That's all, Nama. So net electric field will become 0. Okay. So this is what happens if a conductor is present in an uniform electric field. So therefore, inside this conductor, total electric field will become 0. Are you able to understand? Okay. So therefore, what I say? Therefore, I say that dielectric constant of a conductor, dielectric constant of a conductor is infinite. This is what I say. Clear, ma? So because of this is what is happening here, if a conductor is placed in a uniform electric field, so this electric field, this one, all these electric fields, they get cancelled with each other. Clear? And what is the electric field inside the conductor? Electric field inside the conductor has become 0. Are you able to understand, ma? So therefore I say dielectric constant of a conductor is infinite. Now what do you understand by dielectric constant? Dielectric constant is also written as K, or you can also write it as ER. Relative permittivity is also called as dielectric constant. So dielectric constant of a conductor, I have written infinity. Now can you say what is the meaning of that infinity, ma? What is the meaning of that infinity? Can you say, anybody? So if a conductor, say, ma. Say it. I did not understand what you are saying. What are you saying? Concept have you understood? Electric field inside the conductor is 0. So therefore I have written dielectric constant of a conductor, which is called K. It is also called as ER, relative permittivity. It is infinity. So these values of a conductor, they are infinite. What is the meaning of this one? It means that, so any conductor has an infinite ability of obstructing the electric field inside its volume. That is the meaning of this one. So conductor, is it allowing electric field inside this volume, ma? Conductor, is it allowing electric field inside its volume? It is not allowing. Clear, no, ma? So it has an infinite ability to oppose electric field inside its volume. That is the meaning of this one. Okay. Come on, make a note up to here. So what is meant by K, ER of a conductor is infinite? It means that conductor has infinite ability to obstruct electric field inside its volume if placed in electric field, if placed in external electric field. Okay, ma? So that ability we call it as a dielectric constant of a material. Are you able to understand? And dielectric constant of air or vacuum, okay, ma? So it is equal to 1. Okay, and a dielectric constant of a conductor is how much? A dielectric constant of a conductor is infinite. So for remaining every body, dielectric constant lies between 1 and infinity. Okay, ma? For remaining all the bodies, whatever, whether they are conductors or semiconductors or whatever may be the type of bodies, dielectric constant always lies between 1 and infinity. This is the minimum value which is possible. This is the maximum value which is possible. Okay, ma? So first of all, make a note up to here. So next we will study about types of dielectrics. Types of dielectrics. Okay, ma? So types of dielectrics. So basically, dielectric is nothing but insulator, that's all. Dielectric, I can call it as an insulator. But definitely we cannot say insulator also, because the dielectric constant varies from material to material. Okay, ma'am. So two types of dielectrics are existing. First one, which I call it as polar dielectric. Okay, ma'am. And the second one is non-polar dielectric. Okay, ma'am. So what is meant by polar dielectric? Polar dielectric means, so in a single molecule of this dielectric, single molecule, or you can call atom also if it is an element. Okay, ma? So in a single molecule of this dielectric, what is happening? The center of positive charges, and center of negative charges does not coincide with each other. Okay, ma? Each other, even if no electric field is applied. Okay, ma? So this is called as a polar dielectric. Okay, ma? For example, if you take molecules like a carbon dioxide, okay, ma? So in this type of molecules, the total positive charge center and the center of negative charges, they are not coinciding with each other. What is meant by positive charges? For example, if you take a molecule, clear, ma? Nucleus will be present at the center, no? Nucleus is present at the center and electrons are revolving around this nucleus. So positive charge is present here, and the center of all the negative charges also should be present at the same position. Clear, no? But in some molecules, center of positive charge and center of negative charges, they does not coincide with each other. Okay, ma? It means molecule itself is behaving like a natural dipole. In electrostatics, we have studied electric dipole, nama. What is meant by electric dipole? Two equal and opposite charges separated by a small distance is called as electric dipole. Are you able to understand, nama? For example, this is minus q and this is plus q. Clear, nama? So these two charges separated by a small distance of 2a. So therefore, dipole moment P dash is equals to q into 2a dash. This is called as electric dipole moment, nama. So here also this molecule is also giving some net dipole moment. Why? Because it's a positive charge and negative charge, they are not coinciding with each other. So total positive charge center is present here, total negative charge center is present somewhere here. This is negative charge. So positive charge and negative charge, they are separated by a small distance of 2a. So this type of naturally present molecules which have a natural dipole moment, that we call them as polar dielectrics. Are you able to understand, ma? So polar dielectric means even if you don't apply any electric field in these molecules, they will have a natural dipole moment, because center of positive charges, negative charges, they are not coinciding with each other. Okay, ma? So then we have non-polar dielectric. So what is meant by non-polar dielectric? In non-polar dielectric, so naturally the center of positive charges and negative charges, they are coinciding with each other, and naturally there is no presence of dielectric moment. That is a moment of electric field is not present. Clear, nama? So therefore what I can write here, make a note of this one. Here naturally dipole moment is 0. Naturally dipole moment is 0 if external electric field is absent. What is the meaning of this one? It means that the center of positive charges and center of negative charges, they are coinciding with each other. Okay, ma? So natural dipole moment is absent. So that is called as a non-polar dielectric. Okay, ma? Now let us study what happens if I place a dielectric in between the plates of a capacitor, which is a charged capacitor. Okay, ma? So let us see. Okay. So therefore, see now. So this is plates of a capacitor. So this is having a positive charges. This is a charged capacitor, and this plate, inner surface of this plate is having negative charges. Are you able to understand, ma? So let q amount of charge be present on this one and minus q amount of charge is present on this one. Surface charge density of this one is plus sigma. Surface charge density of negative plate is minus sigma. Are you able to understand, ma? And what is the direction of electric field? Electric field will be traveling from positive plate to negative plate. So this is the external electric field, or just you can calculate, just you can say electric field inside the plates of a capacitor. Okay, ma? So this is the electric field. Now what I am doing is, inside these plates I am placing a dielectric. Okay, ma? I am placing an insulator. Okay, so this is positive. Okay, ma? And this is negative. Okay, so immediately electric field is present here, no? Electric field is present here, and here also there is existence of electric field. Are you able to understand, ma? Now what about electric field inside this dielectric? Can you say? What about electric field inside this dielectric? So here also there is one external electric field. External electric field is how much? External electric field is E0, developed because of the charged plates of a capacitor. Okay. Now in this external field, if I have placed a conductor, then what happened? Total electric field inside this conductor has become 0. Now I am not placing a conductor, I am placing a dielectric. Now can you say what will happen? Anybody? If I place a dielectric, then what will happen? Clear, ma? So what happens is, if you are placing polar dielectric, what is meant by polar dielectric, ma? Polar dielectric means molecules naturally has some dipole moment. That is called as a polar dielectric, no, ma? So for example, if you take a polar dielectric, clear, ma? Every single molecule has some net dipole moment. Every single molecule has some net dipole moment. So for example, if you are taking this one as a molecule, this is negative, this is positive. Similarly, this is negative, this is positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, and positive. So this is the arrangement of molecules of polar dielectric if no electric field is applied. Okay, ma? But if electric field is applied, then what will happen? All these molecules, they will align themselves in the direction of electric field. How they will align themselves? So negative, positive, negative, positive, negative, positive. Clear, ma? So negative, positive, negative, positive, and negative, positive. So this is the arrangement of electric field. This is the arrangement of molecules of a dielectric if external electric field E0 dash is applied. Are you able to understand, ma? So here also same concept is happening, no? So this is the external field which is applied. So total molecules which are present inside this dielectric, they will align in the direction of electric field. So how they will align with each other? So molecules, they get aligned like this. Are you able to understand, ma? Previously, when there was no electric field, they were present in random order. So they were not present in a particular order, but now they are present in a particular order. So this becomes minus, this becomes plus, minus, plus, minus, plus, minus, plus, this becomes minus, plus. So this will be the arrangement of dielectric molecules when it is placed in external electric field. Okay, ma? Now, what is the direction of these molecules, ma? Molecules are arranged in which order? Molecules are present such that positive charges are present in the direction of electric field. Negative charges are present in the opposite direction to the direction of electric field. This is the arrangement, no? So if molecules are arranged like this, then what can you say about induced electric field? Can you say anything about that one? If molecules are arranged like this, such that all the positive charges, they are present in the direction of electric field, and all the direction of negative field, negative charges, they are present in the opposite direction to the direction of electric field. What about induced electric field? Induced electric field, first of all, is it present or not? And if it is present in which direction? Can you see? Induced electric field, first of all, is it present or not? This is a dielectric. Okay, ma? So, induced electric field, is it present or not? That is my question. Okay, ma? So, this is the external electric field E naught. Okay, ma? So, induced electric field, is it present or not? Definitely it is present, no? So, this is positive side, this is negative side. All the positive charges are present on one side. All the negative charges are present on another side. So, this side has become positively charged and this side has become negatively charged. So, what is the direction of induced electric field? The direction of induced electric field will be in this direction, in opposite direction. Okay, ma? And the electric field, external electric field was present in this direction and induced electric field is present in opposite direction. Okay, ma? So, but in the case of dielectric, or insulator, so E external, or you can call it as E naught, is much greater than E induced. Can you say what is the reason? Okay, ma? In the case of conductor, what we have studied, in the case of conductor, induced electric field is equal to external electric field. This is what we have studied, no, ma? Are you able to remember what we are discussing here? In the case of conductor, what we have studied, in the case of conductor, induced electric field and external electric field, magnitude wise they are equal and opposite. Magnitude wise they are equal and direction wise they were opposite. But here what we are writing, in the case of dielectric or insulator, external electric field, this external electric field, it is much greater when compared to induced electric field. What is the reason? What can be the reason, ma, here? So, why the strength of induced electric field is very, very small? Can you say? Why the magnitude of induced electric field is very, very small? So, E induced is very small. E induced is very small because insulator does not have free electrons. Are you able to understand, ma? In conductor, this induced electric field was because of free electrons. So all the free electrons, they were deposited at one side and all the positive charges, they were deposited on the other side. So induced electric field and external electric field magnitudes, they were equal. But in the case of insulator, this arrangement of charges, this is not because of free electrons. This is just because of the natural dipole moment which was present in the polar dielectrics. Okay, ma? So therefore, induced electric field is much less when compared to the external electric field which was present previously in between the plates of this capacitor. Are you able to understand, ma? So therefore, diagram wise, how can I draw? Diagram wise, I can draw a diagram like this. Okay, ma? So listen very, very, very carefully, ma. If you don't understand a small point, then you will not understand the total concept of this one. Clear, ma? So this is the external electric field, which is because of plates of a charged capacitor. Clear, ma? And out of many lines, only few lines enter into this dielectric. Okay, ma? Only few lines enter into this dielectric. What is the reason? Reason is again same. Okay, ma? So this induced electric field is in opposite direction to the direction of external electric field, no, ma? So external electric field is in this direction, induced electric field is in opposite direction. Okay, so these two electric fields, they will cancel up to certain level. In the case of conductor, these two electric fields, they were cancelling 100%. Are you able to understand, ma? In the case of what you called conductor, external electric field and induced electric fields, they were cancelling 100%. But here 100% cancellation is not possible. Some of the electric lines will get cancelled with each other. Is inductor. All of you, have you understood, ma? Clear? So this is the difference between what is called placing of a conductor and an insulator in between the plates of a capacitor. Okay. First of all, make a note up to here. So this side, have you understood, ma? Or shall I explain this one once again? Okay, ma? So if you are placing a conductor, what will happen? If you are placing a conductor, this condition is satisfied. External electric field inside the conductor is in this direction. Induced electric field is in this direction. And magnitude wise, these two are equal. They will get cancelled with each other. But in the case of insulator, so induced electric field magnitude is very smaller when compared to the magnitude of external electric field. So they will not get cancelled with each other. Okay. So therefore, some of the electric field is present inside the insulator also. Okay. Make a note of this point. So therefore, what I will write is, okay, ma? In conductor, electric field inside, or I will write here, electric field inside the conductor, it is equal to 0. Okay, ma? But in insulator or dielectric, electric field inside the insulator is not equal to 0. Okay, ma? Why it is not equal to 0? Because it is not getting cancelled 100%, no, ma? Only some of the external electric field is cancelled, remaining electric field is not cancelled, because induced electric field is much smaller when compared to external electric field. Okay. So therefore, E electric field inside the insulator, can you say how can I calculate, ma? Electric field inside the insulator, how can I calculate? Can you say? So in conductor, electric field inside the insulator was 0. Okay. But in the case of dielectric, electric field inside the insulator, how can I calculate? Can you say, anybody? Come on. Oh my God, very simple, Nama. So external electric field is E naught. Induced electric field is E induced. That's all, no? So these two electric fields, are they in same direction or are they in opposite direction? External electric field and induced electric field, they are present in which direction? Same direction or opposite direction? Definitely opposite direction, no? So these two electric fields, they will get cancelled with, they will get subtracted. So the remaining electric field, we call it as E inside. So here I am seeing only two lines, no? These two lines, we call it as electric field inside this insulator. That is the meaning of this one. Are you able to understand? And for electric field inside, we have one more relation which is called as E naught divided by K. This relation also you have to remember. Okay, ma? Where K is called as dielectric constant of a material, or also you can call it as ER, which is called as relative permittivity. And what is meant by dielectric constant? Ability of a material to obstruct electric field is called as dielectric constant. Make a definition of that one also. So what is K value here? K is equals to ER. First of all, we will define this one. Ability of a material to obstruct electric field inside its volume, if placed in external electric field. Clear, na? So this is called as K value. Okay. So therefore, if any material, if it is placed in electric field, then how can you calculate E value, electric field inside that material? That is given by E naught divided by K. Electric field inside a material is how much, ma? E naught divided by K. Okay. So now by using this one, what is the K value of a conductor, ma? Just now we have discussed, no? K value of a conductor is how much? Come on. K value of a conductor is infinite. Why it is infinite? Because it cannot allow any electric field of lines. 100% it will obstruct all the electric field of lines. So its ability to obstruct electric field is infinite. Are you able to understand? Now place here. So therefore, electric field inside a conductor. Electric field inside a conductor is how much? Which is placed in electric field. It is equal to E naught divided by infinity. Okay, ma? So anything divided by infinity is how much? Anything divided by infinity is 0. So that's what we have studied now. So electric field inside the volume of a conductor, it is how much, ma? It is equal to 0. Are you able to understand? So therefore, now for a dielectric, we will do this calculation. For a dielectric, this relation I can use now. Okay, ma? So now let us see. So for a dielectric, what I can write? This relation I can use. So therefore, what I can write? I can write electric field inside a dielectric is equals to, so external electric field minus induced electric field. Are you able to understand, ma? So therefore, electric field inside, how I can write? I can write E naught divided by K. This is one standard formula. Clear, ma? So what is the total electric field inside the volume of any body which is placed in an external electric field, ma? It is equal to E naught divided by K times. Okay. So therefore, it is equals to E naught minus E induced. Okay. So therefore, E induced will be how much? E induced will be equal to how much, ma? E naught into 1 minus 1 by K. Clear, ma? So E induced is equals to E naught into 1 minus 1 by K. So this is a very important relation. Okay, ma? So this will be the amount of electric field induced in an insulator if it is placed in a electric field of E naught. And what is the K value of that material? K value of the material is K itself. Clear? So that will be the magnitude of induced electric field. So very, very important relation. Make a note of that one. So E induced is equals to E naught into 1 minus 1 by K. Clear? That's all. Okay, ma? So make a note of all this. This was the equation which I got. So see, ma. So this is the plates of a capacitor. This is the insulator. Okay, ma? So therefore here, these are the positive charges which are present on the plates of a capacitor, and these are the negative charges which are placed on the negative plate of the capacitor. And here I have external electric field, that is electric field in between the plates of the capacitor. This is the electric field. Are you able to understand, ma? So therefore, what is the surface charge density here? I can call it as Q. Surface charge density I can call it as sigma plus sigma, and surface charge density on negative plate of the capacitor is minus sigma. So plus sigma and minus sigma. Similarly, because of dielectric, what is happening? Because of dielectric, so all the negative charges, they have come on one side, and all the positive charges, they are deposited on the other side. It means electrons, they are not traveling. So this dipole molecule itself, it is aligning in the direction of electric field, no, ma? Such that all positive charges are present on one side, all the negative charges, they are present on another side. Okay. Now let us see what is the effect of this one. Klima? See, ma, basically why we are using parallel plates in the case of a capacitor, can you see? Already we have discussed this one previously, no? Why we have used parallel plates for a capacitor? Single body is also a capacitor, no? So any body which is charged, that is also a capacitor. Are you able to understand? But what is the reason that we are placing parallel plates? Can you see? Reason for placing parallel plates is that potential decreases. That's all, Nama. So on this plate, what is present? On this plate, positive potential is present, plus 10 volts is present. Okay, ma? And on this plate, minus 10 volts is present. But this plate is present at a small distance from this one, Nama. So the potential on this one acting is how much? It is, for example, minus 6 volts. So the potential which is acting because of this negative plate on this positive plate is minus 6. because it is present at a small distance, no? So therefore, what is the net effective potential of this positive plate now? 10 minus 6 is equal to 4 volts. So potential decreases. If I place two oppositely charged plates side by side, the potential of the positive plate decreases. If potential decreases, electric field also decreases. If electric field decreases, I can supply more charge to this one. That is the reason which we have discussed previously, no? That is the reason why we are placing two plates very near to each other. Are you able to understand now? So same concept is happening here also, no? Same concept, is it happening here also or not? That is my question. Can you see? Happening here also or not, ma? How can I say? See, ma, these are the positive charges and these are the negative charges. So negative charges will give a negative potential on the positive plate. Similarly, these positive charges, they will give a positive potential on negative plate. So finally, potential between the plates decreases, no? Correct or not? So because of this negative plate, negative charges, potential on positive plate decreases. Similarly, because of this positive charges, what you call negative potential which is present on the negative plate decreases. So therefore, what will happen? Therefore, because of induced charges, what will happen? Potential difference between the plates decreases. Okay, ma? So if potential difference decreases, what happens to E value? E value also decreases. Electric field also decreases, no, ma? Electric field also decreases. If electric field decreases, then what will happen? Then you can add more number of charges. Are you able to understand? Because C is equals to Q divided by V, no, ma? C is equals to Q divided by V. So if V value decreases, C value automatically increases. So therefore, if you are placing a dielectric, therefore what is happening to the value of capacitance? Value of capacitance increases. Why value of capacitance increases? Because as you go on adding charges on the plates, its potential does not rise so easily. Why potential does not rise so easily? Because a dielectric is reducing its potential, no, ma? So therefore, capacitance of the capacitor automatically increases. Okay, ma? So this is the advantage of placing a dielectric inside the plates of a capacitor. Its potential difference decreases, capacitance automatically increases. So now this is the relation which I got, no? What is the relation of external electric field I got? Induced electric field. So E induced is equals to E naught into 1 minus 1 by K. So this also tells the same concept, no, ma? This point also tells the same concept. So induced electric field, how I can write? Induced electric field can be written as E naught minus E naught divided by K. Clear, ma? So total electric field, is it increasing or decreasing, ma? E naught minus E naught by K means total electric field induced. Is it increasing or decreasing? What can you say? Decreasing, no? Because E naught minus E naught divided by K. So induced electric field is definitely less than the electric field which is present outside the capacitor. Are you able to understand, ma? Okay. So first of all, make a note up to here, and this one you can write in your own words. So what you can write? Because of negative charges, potential in positive plate decreases. Similarly, because of this positive charges, negative potential on the negative plate decreases. So finally, potential difference decreases. If potential difference decreases, E value also decreases. If E value also decreases, capacitance of the capacitor will increase. So therefore, I can add more number of charges onto this capacitor. Okay, ma? So therefore, see, ma. So these are the surface charge densities. Positive surface charge density present on positive plate, negative surface charge density present on negative plate. Similarly, the charges which are inside the dielectric, they are very small when compared to charges which are present on plates of a capacitor, because this is an insulator, no, ma? So therefore, here I will call it as minus sigma induced, and this is plus sigma induced. Okay, ma? So surface charge density of induced charges, negative surface charge density. This is the positive surface charge density because of positive charges which are present on one side of this insulator. Okay. So therefore, same relation I can write like this. Okay, ma? Sima, what is the formula for electric field inside the plates of a capacitor? Electric field inside the plates of capacitor is sigma by E naught only, no ma? In Gauss law we have studied this one. Do you remember? Electric field inside the plates of a capacitor is how much? E is equals to sigma by E naught, where sigma is equals to charge per unit area. Q per unit area is called as sigma, okay ma? Which is called as a surface charge density. Now, therefore, how I can write? I can write E induced is equals to E naught minus E naught by K. Clear ma? E induced can be written as sigma induced divided by A is equals to E naught can be written as sigma by A minus sigma by A into K. This is what I can write. Clear ma? So, sigma by epsilon naught. Sigma E is equal to sigma by epsilon naught, ma? So this is not A, this is epsilon naught. Okay? Epsilon naught. So epsilon naught and epsilon naught, they will get cancelled. Okay? Then again, what is meant by sigma? Sigma is equals to charge per unit area, no ma? So this is what kind of charge? Induced charge. So Q induced divided by area is equals to Q. The total charge which is present on plates of the capacitor is called Q. So Q divided by A minus Q divided by K. So these are the values which I got. So Q divided by A into K. Okay ma? So therefore again A gets cancelled. So therefore what is charge induced on the what you call sides of this insulator ma? So Q induced is equals to Q, if I take common, it is 1 minus 1 by K. Clear ma? So this is also very important relation for the magnitude of charges induced on the sides of this insulator. Okay ma? So on this total area, total surface area on one side of this insulator, how much charge is induced? Minus Qi is induced. On this side, plus Qi of charge is induced. Okay? And from this relation, you can calculate the relation between the total charge which is present on plates of the capacitor and a charge which is induced on sides of the insulator. Okay? So Qi is equals to Q into 1 minus 1 by K. So directly questions can be asked on this one ma, then you can use this relation and you can do the calculation. Okay? That's all. So what is K? K value we know no ma? K value is the dielectric constant of this insulator. K value is dielectric constant of this insulator. Okay? That's all. So make a note up to here, and remaining discussion we will do in the next class. Okay ma? So E induced, how I can write? I can write, so sigma I divided by E naught is equals to sigma divided by E naught minus sigma divided by E naught into K. This is how I can write. Clear ma? So induced electric field is equals to the induced what you call the surface charge density on one side, negative side of this dielectric divided by E naught. So E naught, that is epsilon naught and epsilon naught, they will get cancelled, and sigma can be written as, so charge induced per unit area is equals to charge which is present on plates of the capacitor divided by unit area minus sigma again can be written as Q divided by A into K. So therefore A and A also gets cancelled. So therefore what is the value of Q induced? I got Q induced is equals to Q into 1 minus 1 by K. So this is the relation which I got. Clear now? So this is also a very important relation to calculate. So the magnitude of a charge induced on one side of an insulator if it is placed in an uniform electric field. So charge induced is equals to Qi is equals to Q into 1 minus 1 by K. That is our answer. Okay, ma'am? So make a note up to here, then we will study about capacitance of a capacitor when this dielectric, if it is placed in an in between the plates of this capacitor. Okay, ma'am? That's all.